All right, so the fifth and final talk in this session is the distinguished paper on covering all the bases, type-based verification of test input generators. It's by Zhou, Ashish Mishra, Benjamin Delaware, and Suresh Jagannathan, all from Purdue. And Zhou will give the talk.
Oh. Okay, thank you for your introduction. So, my name is Zhou. I'm happy to introduce our work covering all the bases, type-based verification of test input generator. So this is a joint work with Ashish Mishra, Benjamin Delaware, and Suresh Jagannathan from Purdue University. So consider a program fx. It uses a black circle to indicate the output of the program. So if we want to try to verify the safety correctness of this program, it means that first we have a safety specification file. And if parts of the output, the fx, is out from the specification, it means this program is unsafe. On the other hand, if the specification is strictly larger than output of the program, that is okay, because we treat the specification file as an over-approximation of the program outputs. But what happens if we do that in another way? We treat the specification as an under-approximation, and we somehow ask the output of the program need to cover the specification file. So actually, we already have this kind of a coverage verification. Let me introduce to you. In the imperative language, typically people use the program logic, like the whole logic, to verify the safety correctness, where we have the precondition P and postcondition Q are interpreted as over-approximation. So recently, people are here introduce the incorrect logic, and the pre and postcondition are interpreted as under-approximation, and incorrect logic can prove a program indeed buggy, so it means that the behavior of the program can cover some buggy case situation. On the other hand, in the functional language, people use a type like the refinement type to do safety verification, and the qualifier phi in the type are also being interpreted as over-approximation. So what is the analog in the functional language of the incorrect logic? So that should be what we call the coverage types, where this qualifier phi is interpreted as an under-approximation. But what kind of a problem can this coverage type solve? So that's exactly the topic of our paper, type-based verification of test input generators. So we verify the coverage correctness of test input generators. So let's start from a motivating example. Consider a tree data type consists of the leaf and node. We want a test generator we call the BST gen return binary search trees, we call BSTs, whose elements are in the given exclusive range low to high. So here's the implementation, and we provide several input-output examples. For the given range 7 to 8, the BST gen generates a single leaf tree because there's no number in the exclusive range 7 to 8. Another example, for the range 1 to 5, the BST gen non-deterministically returns 3 different BSTs. Another example, given the range 0 to 3, is returned 2 BSTs. So one question is that, can BST generate all generate all possible BSTs in the given range? Actually, it cannot. So it cannot generate a single leaf tree. Of course, that is a BST, and no his elements are in this given range. It cannot generate the tree have single node contain 1 or 2. So we say the BST gen doesn't generate all BSTs. It means that it cannot cover all the test cases we want it to generate. We lose the coverage. That is bad. So let's do that formally. We use a formula phi, way, low, and high, indicate where the way is the output of the test generator that must be binary search tree, and all elements are bounded in the given range, low to high. And for example, in the specification 503, we have 5 different binary search trees in the set. However, the BSD-gen can only cover 2 of them. So if we just focus on the safety correctness, we ask if BSD-gen is safe with respect to phi, and we actually interpreted the specification phi as an over-approximation. And our verification asks if all the outputs of the BSD-gen may only be in phi. So the answer is yes, that is safe. However, if we focus on the coverage correctness and we interpreted the specification as an under-approximation, and we require the outputs of BSD-gen must cover all the trees in phi. So in that sense, the BSD-gen is not correct. In general, if we want to verify the coverage correctness instead of the safety correctness, we need to interpret the specification as under-approximation instead of the over-approximation. And we need to perform a mass-style verification instead of a main-style verification. So in order to do that automatically, we introduce our coverage type system. So the rest of talk is structured as the following parts. First, we introduce the difference between our coverage type system and the safety refinement type system, and the formalization and type soundness theorem, the typing algorithm implementation. Finally, we discuss our evaluation. So, because we interpreted the specification differently, from the over-approximation to the under-approximation, we have main 3 differences from the safety refinement type system. It's about subtyping, control flow, and function type. So we first talk about the subtyping. Consider the following 4 specifications. The bottom is included by the leaf, which means only contains a single leaf tree, is included by 503 and included by top. Top means that all possible integer trees. So if we consider a test generator we call the tree-gen have type top, it means that the tree-gen can non-deterministically generate all possible integer tree. So of course, the output of the tree-gen can cover all the BSTs in the 503. Of course, it can cover a single leaf tree, and of course can cover the empty set. So we have the following subtyping relation. The top type is a subtype of others. So here we show the subtyping order. You can see the coverage type inverts the standard subtyping relation. In the safety refinement type system, you can see the order of subtyping is inverted. So the next thing we want to highlight is how the coverage type system deal with the control flow. So here we show this correct implementation of BSD-gen. The correct means this coverage correctness. And this O+ indicates a non-deterministic choice operator. It consists of 3 different branches. The first branch only returns a single leaf tree. The second also returns the single leaf trees but under different condition. And the third one, for example, we call that in with the 03, will non-deterministic return the following 4 BSTs. So if in the safety type system, we need to verify each branch against a given specification phi because we need to guarantee all branches are safe. But that is not true in our coverage type system. For example, if we focus on the second branch, just return single leaf tree, of course, it's a single leaf tree cannot cover the 5 trees in 503. So actually, we need to ensure the combination of all branches cover all expected values. It means that here we have 3 branches. Assume each branches have the coverage type phi1, phi2, and phi3. We need to ensure that the phi can imply the disjunction of phi1, phi2, and phi3. The third point is about the function type. I think that is the most interesting thing in our coverage type system. Let's consider the BSD-gen implementation. So what is the function type BSD-gen should have? So of course, it should have the 2 parameter type for lower bound and higher bound and 1 return type. And intuitively, the return type need to specify the coverage guarantee over the given parameters So that is a coverage type, phi, low, high. On the other hand, the parameter type need to allow any application with valid arguments. For example, it need to allow the BST gen over 0 and 1, but disallow all application with invalid arguments. For example, the BST with 3, 1. The lower bound 3 is even greater than the higher bound 1. So we require the low is less than high, and that is exactly a safety correctness. So here, as we show here, that is a function type of BST gen whose have over-approximate parameter types and under-approximate return type. It means that the function type actually mix both over-approximation and under-approximation. We have formalized a core calculus with coverage types, and our type soundness theorem say for any well-typed term with respect to a formula phi, and all values satisfy phi can be reached from E. And as we show in this figure, it means that all value E can reduce to can cover phi. That's quite different from the safety refinement type system, where the specification will cover all the value E can reduce to. So you can see in this implementation, the left-hand side and right-hand side are inverted. We also designed our typing algorithm that is a standard bidirectional typing algorithm, have type synthesis and type check, and the decidable SMT-based subtyping algorithm. And finally, we implement our coverage type checker Purdue for pure OCaml programs, itself also written in OCaml code, and uses this array as a backend solver. So, in the evaluation, we are curious about 4 research questions. The first is about the effectiveness. Can Purdue verify input generator over diverse data type and non-trivial properties? So we evaluate Purdue over 14 realistic handwritten input test generator from property-based testing, and which involve diverse data type, list, tree, queue, strings, heap, and sets, and non-trivial properties, especially the structural property includes the sorting, the complete tree, and balance property of red-black tree. Here I can show you example of this specification. It's about the list gen is required to output the generator cover all lists whose length is less equal than the given size. The second question is about the efficiency. Can Purdue verify input generators in a reasonable amount of time? As we show in this bar chart, the type checking time of Purdue is no longer than 13 seconds, so that is efficient. So take a look at this benchmarks. It take a longer time. It's a size BSD gen, and it have 5 different branches and 20 local variables. Remember how we deal with this control flow. We need to disjunct them together. So the more branches you have, it means that the larger query you have, there will take a longer time. And the third question is about the scalability. Can Purdue verify complex input generator? We have a case study about the simple type nominal calculus term generator consists of 13 auxiliary functions. And we also verify it against the non-trivial property. We ask it can cover all val type terms. So the val type here is inductively defined by some typing rules. So Purdue can successfully verify this kind of a test generator. And the last question is about the utility. So we introduced this 2 kinds of verification, safety and coverage. But the question is that, are the safety generator always a coverage complete? So consider this coverage specification, and the safety specification and coverage specification who have the same qualifier. And if a safe test generator whose output can already cover this coverage specification, so it means that we don't need Purdue at all. There's another situation. The safe generator is actually lose some coverage. So in that case, we do need Purdue. So we have our evaluation, we have the experiment for this. We reuse our property-based testing benchmarks, and we use the existing refinement type-guided component-based synthesizer to synthesize multiple safe programs. And verify this synthesize the safe programs over a coverage type system. You can notice that this specification we use here have the same parameter types. We just flip the return type from the over-approximation to under-approximation. So results show that the 76% to 99% safe synthesized program don't pass our coverage type checking. It means that we do need a coverage type checker. So in summary, we focus on the complete correctness of the test input generator, and we introduce our coverage type system, have 3 difference from the safety refinement type system. Please scan the following QR code to check our artifact, where artifacts is reusable and available. Thank you. It's open for questions.
Great, we have lots of time for questions.
Hi, I'm Elias again, National University of Singapore. Really nice work and really nice talk, really enjoyed it. Kind of an open-ended question, have you considered reason about the distribution of the outputs using some version of the refinement types?
Yeah, it's a very great question. So you ask about if I consider to verify the distribution, in my mind, maybe especially the fairness, or if all this test generator have a uniform distribution. Right. Yeah, I think that is a direction we're consider. Maybe that is our future work. There's a lot of the things we need to consider, for example, how to encode the probability or distribution in a type system, how to deal with the control flows. So yes, that is exactly what the thing we want to do in the future.
Thank you.
Hi, this is Django Lee from KAIST. I had a question about your evaluation. So you mentioned that existing tool generation mostly did not have full coverage, and my question is twofold. So first is, what was the main reasons that existing tools does not have coverage? And the second is, if your tool detects that the existing tools does not have coverage, does it suggest a way to fix that?
Oh, you mean that you question that if some test generator fail our coverage test, is there we provide some suggestion to them to refine
Yes.
this coverage types? Yeah, I think this is a great question, and that is something we want to do. And I think that is a challenge question, because even in this safety refinement type system, if a program fails this type check, it's hard to find the counterexample, because the verification say if you pass the verification means the program is correct, but if you don't pass verification, it's not necessarily implies the program is wrong, because maybe we do some approximation. So, but I think that's a great question that will be in our future research. We'll try to find the counterexample to help the user to redefine these test generators. Does that answer your question?
Yes, thank you.
All right, let's thank again.
Yeah.
So before you go, I have just a couple of further announcements. First, let's congratulate all the Distinguished Paper Award winners again.